we are going to discover how to differentiate under the integral sign. Now we'll learn how to do that. We'll also learn why it's important, and if I have time at the end, I'll show you why it works. Okay, this idea is known as Leibniz rule. Okay, so sometimes in applied mathematics, we come across a function that's defined as an integral. And in particular, sometimes these integral type functions can't be expressed in terms of so-called elementary functions. So if you look at that integral from 0 to x of e to the minus u squared du, that can't be integrated. E to the minus u squared cannot be integrated in terms of so-called elementary functions. Okay, I mean you can expand e to the minus u squared as a power series and then integrate term by term, but we would not call this a so-called elementary function. Okay? Now, it turns out that these kinds of integral type functions occur so often that we actually define them as standard functions of x. So here's a function that you may have come across called the error function. Anyone seen that before? Heard of the error function? Anyone? Yes? Well, that's used in lots of different places. In particular, this form here is used in solving certain partial differential equations involving diffusion. Now, another important function defined by an integral is the so-called Laplace transform. So suppose I've got a function, little f of t, satisfying certain conditions. What the Laplace transform does is it takes your little f, it multiplies by this exponential function, and then you integrate over this half line with respect to t. Okay, so there's two kinds of notation, sort of this curly L of f of t and this big F of s. Now, you can see in this integral, t is the dummy variable, but what happens with this s? Well, the s doesn't change. Well, I guess it doesn't disappear if you can do this integral. So actually, that boxed expression is a function of s. A function of s. We'll look at this a little later in the semester, these Laplace transforms. So what we're going to do today is learn how to differentiate functions that are defined via integrals. And the method is known as Leibniz rule. The question is, why would you want to do that? Well, I can think of two reasons for us to motivate our study in this area. Firstly, if a function defined by, through some sort of integral is useful for modeling purposes, for example, solving PDEs or something like this, then it would seem to make sense that the derivative would also give us insight into the problem under consideration. And secondly, Leibniz rule, as we'll see, can be applied to evaluate very challenging integrals. So it's a little bit of a strange situation where, as we'll see, you're actually using differentiation to integrate something. But I'll show you what I mean as we go along. Okay. This is the most basic version of Leibniz rule. Here's a picture of Leibniz, as you may know, one of the early contributors and instigators of calculus. Okay, well, if a and b are constants and some function, say of two variables, and its partial derivative with respect to the x variable in this case, are continuous on some rectangle like this, then if I have a function I defined by this integral here, then the derivative, all I really do is I push the d dx inside the integral sign and change the straight d's to curly d's. Okay, so in the subscript notation, this would just be the following. Okay? So remember here, the t is the variable that we're integrating over, and the x, well, the x is the independent variable. Now, some of you may have the x and the t switched around in your notes. Okay? I reposted something, I think yesterday or the day before, where it's not x comma t in your f, it's t comma x, just to keep it alphabetical. Okay, now I'll come back and prove that at the end if I have time. The proof isn't too difficult. So let's look at how we can use this Leibniz rule for differentiating an integral. This one's a real basic example. Here we've got a function of x defined in this way. Calculate the derivative. Now, it would be tempting to try to integrate cosine tx over t with respect to t, but how are you going to do it? How are you going to do that? Imagine x is a constant in the integrand. What's the antiderivative of cosine tx over t? Well, so what we're going to do is just show how we can calculate the derivative using this. And the method for this basic case is the following. So I'm differentiating. Let me just put this in brackets. Now, the method, of course, you just move the d dx inside the integral sign and change it to a partial. Okay, that's like the computation, right? It's very, very simple. Oops, very simple that I can't do it. Okay, so you move this inside and change it to a partial. Now, why do I need to change it to a partial derivative? Because this is a function of two variables, right? Okay, so it doesn't make sense to have just d dx there. Okay, so here I've just used Leibniz rule 1, L1. Okay, so let's compute that partial derivative and then see where that takes us. Okay, so I want to compute the partial derivative of this with respect to x. So I hold t constant, right, and differentiate with respect to x. So cosine is going to go to negative sine, and that t is going to come to the front. Okay? So now I can cancel those t's off. And I do know the integral of sine of tx with respect to t. Okay, imagine x is constant and integrate with respect to t. Okay, so I can integrate this now because these things have cancelled off, which is really nice. So let's integrate minus sine tx with respect to t, holding x constant. So I'm going to get a cosine tx, almost like what I started with. And I'm integrating with respect to t, so I'm going to divide by x. Okay, so let's just plug in for t equals 2 and t equals 1 in the usual way. So that I'll get cos 2x, I'll put it in brackets just for completeness, and cos 1x. Okay? So very similar for a lot of these kinds of questions. You just push that d dx or dd whatever inside the integral sign and change it to a partial. Hopefully, when you take the partial derivative, the situation simplifies. You can see we've got some cancellation in the third bottom line, and that enabled us to actually perform the integral. Okay, so that's a fairly standard question. Actually, pretty basic, I've got to say. All you have to do is push this in and take the partials and then do the integral. All right, here's a slightly more difficult one. This is the more general version of this Leibniz rule. Okay, I'm going to call it L2. Instead of having constants in the limits of integration like we did here, imagine that a and b are functions, differentiable functions. So, you know, u might be root x and v might be x squared or something like this. Okay? Now, in that case, it gets a little bit harder. You still push the d dx inside the brackets, but you've got two extra terms here. Okay? Now, in the previous L1 situation, u and v were just constants, so their derivatives are 0, so there's no extra terms in the L1, right? So hopefully you can see how L1 is a special case of L2 when u and v are just constants. Okay? Now, this is a lot to remember. It actually relies to prove that you can. I'll leave it for you to prove the more general case. I'll go back and do L1 if I have time. But this is just basically applying L1 and the chain rule. Okay, we talked about the chain rule last week. Okay, how can we use this then? Well, here's an example. If a function of x is defined through this integral, calculate the derivative of that function. Okay, so it's a standard application of this. Okay, so let's see how we do it. So here, our u of x is root x. Our v of x is x. And our function is this. Okay, so what do we need? Well, to apply this, we just d dx here, push that in, that gives you that term. And we need the derivatives and f evaluated at the upper and lower functions or limits of integration. Okay, so let me show you how that works. Okay, L2 gives the following. Okay, that's the first term. And now we want to get these terms here. So we want to differentiate and plug in u and v. You replace t with u and v in your f. So we're going to get something like the following. So if I replace t in our f with x, I'll get the following. And then I want to multiply that by the derivative of x, which is just 1. Okay, so that term is just here. Okay, so now I want to take away the other sort of situation. I replace t with root x. And I want to multiply this term by the derivative of this lower limit of integration. So the derivative of root x is just 1 on 2 root x. Okay, so now it's up to me to just clean up. Do that first term, see if I can simplify that, and then sort of clean up the algebra over here. Okay, so if I differentiate sine of tx on t partially with respect to x, then what's going to happen? Well, this t is going to come to the front, and I'm going to get a cosine. So cancel, cancel. And here I'm just going to get sine of x squared on x. Now here we're going to get root x times root x, so we're going to get sine x to the 3 on 2 all over 2x. So okay, I'm almost done. All I really need to do now is take care of this first term, this integral. Okay, so to integrate cosine of tx with respect to t, well, cosine's going to go to a sine. And I'm imagining x is a constant, so I'm going to divide by x. So all I need to do now is replace t with x and root x in the first term, and you'll get the following. Okay, so here I'm just simplifying the algebra. Okay, so you probably, if you were doing this, you'd probably add an extra line between the bottom line and the second bottom line, but I've kind of run out of space. Now, how do you remember? How you doing? How do you remember this crazy Leibniz rule? Well, I'm glad you asked. I'm glad you asked. In the class test, you'll get the Leibniz rule, okay? Which is good. Which is very good. Yes. I believe so. I believe so. Okay, so you don't have to remember it, but don't lull yourself into a false sense of security, right? Most students fall over on this question because they mix up the variables or the letters. Okay, oh, dx dt, d dx, what the... okay? That is the challenge, keeping an eye on your variables. You're not always differentiating with respect to x. I know in some questions in the course pack, they flip it around. They say they switch t with x, so that would be a function of t, and you'd be integrating with a dx in there from, say, root t to t. This actually, it seems reasonable, but a lot of students get confused with the letters and the variables. Don't let it be you. Don't let it be you. Okay, here's another one. Now, I hinted at the start that these kinds of Leibniz rules can be helpful for integration. So let me show you an example involving this. So this isn't a really super applied example, but it's a nice application to show you how you can use this idea in integration via differentiation. Okay, so here I've been given this I guess, function. Now, this is slightly different to the case that we looked at before because it's an improper integral, right? You've got an infinity sign in the integral. Now, Leibniz rule still works when you're integrating, you know, from say 0 to infinity or on the half line, as long as, you know, all the integrals, all the improper integrals converge. Okay? So you can see here, this is a case where actually this is a function of alpha. Okay? And we're asked to apply Leibniz rule to show that this integral equals this. Now, if you want to know where did this come from, well, you can make a substitution. X equals root alpha tan theta or something. That doesn't really matter in this context where it's come from. We know it's true. So we want to use that to somehow show this is true. Okay, so let's call this star. And what I'm going to do, I'm going to apply Leibniz rule by differentiating both sides of this given information. Okay, so what I'm doing there is I'm just basically differentiating both sides with respect to alpha. Now, in this middle expression, I can apply Leibniz rule. I can differentiate this right-hand side just by regular calculus. So by L1, let's move this in here. If I differentiate this with respect to alpha, what's going to happen? Well, I've got a power negative 1/2 there. So if I differentiate, I'll get. So, okay. Now, if I differentiate this right-hand side here, I'll get the following. I'll get a minus 4 alpha to the 3 on 2. So I'm taking the given information, start, and just differentiating both sides. To differentiate the left-hand side, I need Leibniz rule. Just push that derivative, the dd alpha, inside the integral. Okay? So let's differentiate in here and see what happens. Well, if I want to differentiate this partially, what happens? Well, it's going to be something like minus 1 all over x squared plus alpha all squared. So you can see how you need to have a good understanding of partial derivatives to do this problem. Well, lo and behold, I've almost got this here. The only thing is just minus sign. So we can just remove the minus signs and we get and so double star holds. Yes. Now that is a reasonable question that you see on class tests, end session, things like this. You're given some information and you're asked to produce some other integral. Okay? Now, doing this integral on its own is not easy. Can you do it? I'm not saying it can't be done by other methods, but hopefully you can see that you're actually differentiating to get a difficult integral, that double star setup. Pretty easy, right? So that's that's a stock standard question that we would ask you maybe in the class test or something like this. Okay, this one's slightly harder. Imagine b some positive number. Use Leibniz rule to show that this integral here is equal to log b. Now, I challenge you, can you come up with an antiderivative of this for each value, each positive value of b? How do you do this using Leibniz rule? How do you do it using Leibniz rule? Well, this actually requires more. We don't know that this is true, right? We're asked to show or prove this. So we can't just sort of differentiate both sides or, you know, work on it that way. We sort of have to start with the left-hand side and then, you know, perform some analysis on it. You know, they mentioned Leibniz rule, so let's just differentiate the left-hand side. So I'm going to define this by some function, say I of b, where b is the variable. And I'm going to differentiate ddb. Okay? So Leibniz L1 says I can just push that ddb inside the integral and change it to a partial. Okay, now we're sort of tacitly assuming that all of these, you know, improper integrals converge. That's okay. We won't be too concerned about that in our study. Yes? So that was using L1 on the right-hand side. So let's differentiate this partially with respect to b. So the minus, that'll be 0 when I differentiate that with respect to b. The minus t will come to the front, and I'll get something like this. Okay, the minus t will sort of cancel, the negative sign will disappear. So I get something like this. So I can cancel those t's off. And now all I need to do is integrate e to the minus bt. Okay, this is like an improper integral, remember, from first year. So to integrate this, I imagine b is my constant here, integrate with respect to t. I'll get something like this. And my limits, t is going to infinity and t equals 0. Okay, I can't put t equals infinity up here. That would be a bit naughty. So, as t goes to positive infinity, when I sort of sub that, you know, take the limit, the first term is going to be 0. And when I sub in t equals 0, I get minus 1 on b. Now, you may be thinking, well, so what? So what? What have we produced? We found the derivative of our function, of our original expression, and we know that the derivative is 1 on b. So why can't I just integrate 1 on b to get I? If I integrate I dash of b with respect to b, I'll get something like log b plus a constant. So you can think of this as like a simple differential equation. So let's integrate this and this. But remember, with integration, we've still got a constant to worry about, a constant of integration. So can anyone tell me how I can get that constant of integration in the bottom line that I've written? I'll be very impressed if anyone can tell me. So this is a constant here. Integrate? Huh? How do you know? But well, if you compare this and this, what do you think the constant should be? 0, right? So how can I show that the constant's 0? Well, maybe this is what you're getting at. If you look up here, what happens if I put in b equals 1, right? That's what you're saying. If I put in b equals 1 in here, so I of 1, I get e to the minus t minus e to the minus t. So that's all 0. So very good. So going back up here, I of 1 equals 0. So this is 0. So we know that star's got a hold. Very good. Okay, now that would be a horrendous integral to try to evaluate. That would be, yeah, if anyone can do it using, you know, I mean, sometimes you can do these things using integration in the complex plane, but you haven't seen that yet. I'd be very impressed if you can integrate that. Now here's a harder exercise for you. This is not a function of one variable, but two. So try to come up with this using similar methods to the example that I've just shown you. So instead of ordinary derivatives in Leibniz rule, you know, f dash, f prime, you would have partial derivatives. What's the setup with that? Well, I'll leave you to discover that for yourself. Aha. Laplace transforms. Who's heard of a Laplace transform before today? Yes? Okay. If you're studying engineering, Laplace transforms, you'll see them all the time. Okay, especially later in this course and probably next year, I would think. Now, suppose I've got a suitable function, little f of t. This is how we define our Laplace transform, assuming that everything's, you know, well-defined and convergent. We're asked to apply Leibniz rule to show that the derivative of this function of s is just the negative of the Laplace transform of t times f of little f of t. So how do we do it? Well, let's experiment. Let's work with what we know and use the Leibniz rule. So we're going to differentiate both sides of this. Differentiate. Differentiate star to form the following. So I'm not going to worry about this middle part. Now Leibniz rule says I can just push this inside and change the d's to sort of curly d's. Okay. So let's do that partial derivative, dds of e to the minus st times f of t. Well, the little f doesn't depend on s at all, so this isn't going to alter our derivative, it's just differentiating this. What's going to happen? Well, imagine t's constant. That minus t from this exponential is going to come to the front. Yes? And if I just rearrange this, I can take the minus sign out the front. I can rearrange the integrand. And look, if I cover that up, this and this are the same, except instead of f of t, you've got t times f of t. So that is just Laplace transform of t times f of t. Okay? So essentially, instead of having a f of t here, we've got a t times f of t here. And that's just the Laplace transform of t. times f of t. Now, later in the course, we'll use that result a lot when we're calculating transforms and solving DEs and looking at vibrating systems and things like this. Okay, so it's always a good idea to have some understanding of where these things come from. Okay, it's Leibniz rule. We don't just teach you Leibniz rule because it's, you know, something to do. It's useful in many cases. Now this is, I mentioned that the L2, the more general version of Leibniz rule, involves the chain rule. Okay? If you do this question, you can see how the chain rule works in this context. I'm not going to do this one. I'm going to leave it for you to do. There is a, I have done this question in one of my videos online. So if you want to have a look, you can. But if you do this question, or if you follow along, you will see how the chain rule works in this more general setting. Okay, that's the motivation behind this problem. So have a look at that on YouTube. I want to go back and show you, give you some idea of why it works. Why does this? Why can you just push the ddx or whatever into the integral sign? Okay. Why? Well, the proof is nothing more than the fundamental theorem of calculus, which tells you that integration and differentiation are two opposite things. That's it. They're reverse processes. That's all it is. Okay? It looks difficult, but it's not. Okay? So let me see if I can squeeze in a proof. Okay, PF stands for proof. Okay, so what I'm going to do, I'm going to start with this and then show that it's the derivative of this. All right, that's all I'm doing. Now, what I can do is integrate that expression, okay, and differentiate it at the same time. So I'm going to integrate this and differentiate it at the same time. By the fundamental theorem of calculus, I haven't changed what I'm dealing with. So let me show you what I mean by that. So what I can do is just write this. And I'm going to change these x's here because this is where my variable is lying now. So I've got a little dummy variable in here. Okay. So that's by the fundamental theorem of calculus. Okay, now what I can do is switch the order of integration and switch these derivatives or these differentials. So what I'm going to do is switch No, it's okay at the moment. No, because this is, so the y here is dummy variable because there's my x variable up there. Okay? Now, again using the fundamental theorem of calculus, what I can do, this is a derivative and this is an integral. So I can integrate what's in this big square bracket. So it's just, now I can go back to an x because I'm replacing x with a y with x here. Ah, sorry. That shouldn't be there. Because this is just f. Okay, so this is not, no subscript here, just f. Okay, well, this doesn't depend on x at all. So when I differentiate this, it's just going to be 0. So this then is just the following. So this is equal to this. So again, so in this line I'm just using the fundamental theorem of calculus.